So last time we discussed design class. In particular, in the design model, unlike in the analysis model, we have to take into account implementation environment, that is, performance issues. So that is why we sometimes need to restructure the design model. That is, by producing a functionally equivalent design model while improving performance, or by, say, optimize it by revising the access paths. If something is accessed frequently, then perhaps you should not jump through several hops to get to it. Perhaps you should add a direct link to it. Collect classes, that is, when the class is really simple with very few attributes and operations, perhaps you can collapse it with another class to reduce the number of classes. Cache or delay expensive computations. So if something is calculated often and it's time consuming, perhaps you should cache the value. That is, you calculate it the first time you need it, and then you store it as an attribute. Later, you just get the attribute. So, or delay expensive computations. That is the example where you have a document with lots of images in it. So, if you load all the images upon opening the document, it may take a long time. So you can load it on demand as the user browses to that particular part of the evaluation here, and it's here. So particular part of the document. So class design, you should strive for high cohesion. That is, a class should do one thing and do one thing well. Should have a single abstract concept and should have operations that support the intent of the class. It shouldn't have a lot of responsibilities. You should have one or a few responsibilities. And low coupling. Coupling is the association with other classes. So it should be associated with just enough other classes to allow it to realize its responsibilities. So, and complete and sufficient, do what the users of the class expect. So if you have a bank account class, you should do withdrawal and deposit. Nothing more than that. And a primitive should have the simplest and smallest possible set of operations to facilitate reuse in the future. It's always easier to reuse a simple class than to reuse a complex class with many operations in its interface. So here's the class design example of optimization for performance. This is the familiar reserve video use case. Allows the staff to reserve up to 5 videos at a time for a member, which is a special customer. Actor is the staff. Precondition is the member has less than 5 videos reserved. And use case begins when the user, that is the staff, selects reserve a video menu item, and the system prompts the staff to input the member number and the video ID. And the staff inputs the member number and video ID and reserves a copy of the video for the member. So here's the class diagram. We saw before. So notice that the staff is not a class in it, because the system does not need to keep track of the staff who handled the transaction. The system only needs to keep track of the customer and the video information. So the staff gets a member number, so he looks up the member object based on the member number and a video ID. So now his job is to take these two pieces of information and establish a link between a rental copy and a customer. Rental copy reserved rental copy and a member. So he needs to establish this link. So now he can get the member from the member number, but he needs to navigate from movie video to rental copy by following this association, has association. And then he can establish a link. So the question is, how to determine whether a copy of a movie video can be reserved? That is, if the copy is already reserved or it's already rented, it cannot be reserved. And given your answer to A, how can the process of determining whether a copy of a movie video can be reserved be made more efficient? That is, you can optimize the design model for performance. So the solution is that first to note is question asks how to determine whether a copy of a movie video can be reserved, not whether a member can reserve a copy of movie video. That is, you're given a video, you're trying to determine if it's available or not. So the member has less than 5 videos reserved is another issue that's not asked in this question. So to determine whether a copy of a movie video can be reserved, we need to check 2 things with respect to the corresponding rental copy object. First, is it currently reserved? Second, is it currently rented? If either of these 2 conditions are true, then it cannot be reserved, and it can be reserved otherwise. So how do you determine if it's currently reserved? So you check if the rental copy object currently have a reserved link. If yes, then it is currently reserved. If the rental copy object currently have a current rental link, then it cannot be. Then it's currently rented out. So it's not available. So you look at essentially these 2 links, these 2 associations, current rental and reserves. So these class level associations get turned into object level links at runtime. So if these links are null, that means there's no link to another customer object with the current rental association and no link to a member object, then it's free. It can be reserved. So how do you speed up the process? Optimize the design classes. Since it can be quite expensive to check whether links exist, and since in some cases both tests need to be done, so because database links, if you check if a database link exists, you need to traverse the entire table to check for links. So it can be expensive. So you can optimize the checking by adding a new attribute status to the rental copy class. The value can be either available, reserved, or rented. It can be enumeration type, and it's set whether whenever a copy is returned, reserved or rented. So now we need to check the value of this attribute to determine whether a copy of a movie can be reserved or rented, instead of checking for links every time. So, of course, the cost of doing that is to update the attribute whenever you return, reserve, or rent a video copy, rental copy. So as long as you remember to do that, then this attribute will reflect the actual status of the rental copy, and then you can just check the attribute. We'll need the status. So this is really a trade-off between you're doing more work when you are doing daily operation. You do this one more step of updating the attribute, and then the later operation of checking the status can be very efficient. But if you do less work, that means you do not update the attribute. You don't have the attribute status in the class. Then you have to do more work later when you need to check the status of the rental copy. So it's perhaps better to do more work during the daily operation, because it's just a simple update operation, and to speed up the query of the status operation. Another optimization, so we're given a video ID to find the rental copies. Therefore, you need to navigate the association from the video object to the rental copy object. Therefore, it can again be an expensive operation, especially if the tables of video and the rental copies are large. If it's a memory operation, following a pointer is very fast, but you need to actually check the database tables and traverse the disk. So that can be very expensive. So you can include an attribute video ID in the class rental copy, so you do not need to follow the link from movie video to rental copy when checking whether a copy is available to be reserved. In fact, if the domain model is stored as a relational database, this would be done anyway to implement the hats association. Remember, the associations in the domain model classes are turned into common attributes, common columns in the database tables. So we see these two optimizations. One is to add a new attribute to avoid traversing the table to check for links. One is to add a new attribute to avoid navigating from one class to another. So both of these two optimizations are unnecessary in terms of functionality. If you don't have these, the system works fine. These are added to improve performance. And this kind of performance optimization is only done at design stage, because in the analysis stage, we don't care about performance. We only care about functional behavior. But in the design stage, we need to be realistic and take into account implementation environments, and hence performance. So now we discussed class design. Now we discuss subsystem design. Okay. So a subsystem organizes artifacts of the design model into more manageable pieces. A subsystem can contain design classes or other subsystems. So this shape here is really similar to the package icon in the analysis model, except you have this little thing here indicating it's a design model subsystem, not an analysis model package. It's not really a standard in UML specification, but it's a common convention. So a subsystem can contain design classes, other subsystems, interfaces, and use case realizations. So we'll see some examples next. So it can be designed as a collaboration of subsystems rather than classes. So it can be represented as a class diagram of subsystems. So it can be hierarchically nested. Subsystems can be used in sequence diagrams. So remember, sequence diagrams, typically you have classes on the vertical axis. So you can use subsystems instead to indicate a more coarse-grained behavior. Allows hierarchical decomposition of a system. So a subsystem can have a behavior described in the sequence diagram, and then can decompose the subsystem itself into another sequence diagram to describe its internal behavior within its contained classes or subsystems. So it can be refinements of packages in the analysis model. So there can be a one-to-one correspondence between an analysis model package and a design model subsystem. But also you can be directly identified in the design workflow. That is something that's in addition to what you have in the analysis model as a package. Or if you don't have an analysis model, if you skip the analysis step and go directly to design, it can be possible if your system is simple. So again, we see cohesion and coupling. So you have try to make the subsystems independent and loosely coupled, but highly cohesive. So we saw this a couple times before. We saw this in the analysis model package design. We saw this in the design class design, and again here in the subsystem design. So it's most cohesive when it does only one thing, and has lowest coupling when it has minimum dependencies with other subsystems. Okay. On the right is the anonymous copy.
It should be 2 cover pages, right?
Yeah, okay, that's fine. So again, we identify we have a trade-off between cohesion and coupling. If you have a very fine-grained partitioning of subsystems, then you have high cohesion, but you are also likely to have high coupling because there may be many links with other subsystems. But if you have very coarse-grained partitioning, you may have very low coupling, but you may have low cohesion also. Because it may have to do many things within the subsystem. So you need to strike a balance between these two. So layers and partitions. So subsystems are often organized in a layered structure. There may be 2 types of architectures. One is closed layered architecture, where each layer can only depend on the layer immediately below it. Another is open layered architecture, where each layer can depend on any layer below it. That it can bypass some layers and jump directly to a lower layer. So it has higher coupling if you have open layered architecture, but less overhead, because you don't have to go through many layers to get to another layer. Closed layer architectures have lower coupling, but more overhead, because you have to jump over multiple layers every time. So it's a trade-off between coupling and really performance. So subsystem partitions. So the layering is a horizontal partitioning of the subsystems. Now, the subsystem partitions are the layering are the vertical partitioning. Partitions are the horizontal partitioning. That is, you can divide up services in one layer into different subsystems, and you have peer-to-peer services within the layer. So usually you have 3 to 5 subsystem layers. In practice, you shouldn't have too many subsystem layers to avoid introducing too much overhead into the system. So it should encapsulate middleware and system software subsystems. So middleware is, say, Corba or Microsoft.NET, and system software is the operating system. So you encapsulate it by designing APIs to wrap the OS and middleware specific APIs, so that when you move to another platform, OS and middleware, you can just modify this one piece of interface instead of modifying the application. So as we discussed before, you have the bridge between the application and the platform. By encapsulating the OS-specific calls in the bridge, you can enhance the portability of the software. So let me see if I have an example. So here's one example of subsystem partitioning, where you have 4 layers: a system software layer, that is operating system services; middleware layer, providing middleware services like distributed communication services, or load balancing, or fault tolerance, or a bunch of stuff that's not in the OS. So application general layer is the layer that's perhaps usable by many applications. And application-specific layer is the layer that's specific to this application. So, for example, if you're developing a financial trading application for Merrill Lynch, then application general layer perhaps consists of the generic trading operations, while application-specific layer consists of those specific logic for this particular company, Merrill Lynch. So that's vertical partitioning of layers. So as you can see, most of these cross-layer connections are closed layer architecture. So you have application-specific layer using the application general layer, the layer directly below it, and all these links are between neighboring layers. But there's one link here from application general layer directly to the OS layer. So this one represents an open layer architecture connection where you bypass the middle layer and go directly to the lower layer. So that can be used to improve performance if the application general layer calls into the OS very often to reduce the overhead of the common case. And also you have the connections between the tiers within the layer. So this is the subsystem partitions horizontally, where you have the application-specific layer has 3 subsystems partitioned horizontally, and there's a connection from this one to this one. But there's no connection between these two because perhaps they don't need to communicate with each other. So here's the ASU package design we saw during the analysis design flow, where we partitioned all these analysis classes into packages. So we had the UI, user interface package connecting to the people maintenance, consisting of the entity classes in the related to maintaining student and professor information, course maintenance, and course registration. So I'm sorry, these are control classes, and these people data and course data are the entity classes. So these are encoded in color. So the yellow parts, so student UI, course UI, professor UI, these are grouped into a single package, user interface. and all the student manager and professor manager control classes are grouped into a people maintenance. Course manager and catalog info manager are grouped into a course maintenance, and course registration consists of the other managers control classes. And then you partition the entity classes into two parts. One is the those related to course data, course section, semester, course offering, and those related to people data. So you can draw the connections between these packages by following the connections in the analysis class diagram. So this is the analysis packages. When you design the subsystems, notice the little symbol here indicating that it's a design subsystem instead of analysis package. So you have a one-to-one correspondence between all these. So each design subsystem corresponds directly to analysis package. Except you have two more. One is the system security, handling non-functional requirements for access control. That is login, password, etc. And report generation for generating various reports by the registrar, by the professor, by the students. So both of these two are not in the analysis model. So because these are really cross-cutting non-functional requirements, that's not directly part of the functionality. So in the analysis stage, you don't care about security. You only care about what the student can do, what the professor can do. But in the design stage, you need to consider that by adding two additional subsystems in addition to the functional subsystems directly related to the analysis packages. And these links can also be directly inferred from the analysis package links, except the new ones where you have to draw the links. So you can see that the system security subsystem is linked to the people data only, because the security is login management. So it has nothing to do with the course data. But the report generation is to use both the people data and course data subsystems, because the report must contain both data. So interface. So interface is the set of operations that are accessible from outside the subsystem, also called the API. As you heard often, application programming interface. So this is what the application programmer sees from the outside. So the interface is denoted as the lollipop shape extending from a subsystem with a name beneath it. So interface specification includes operation names, parameters and their types, and return values. Interface implementation is provided by classes or other subsystems within the subsystem. So if a subsystem has a dependency directly towards it, it's likely that it needs to provide the interface. That is, the interface is designed for the other subsystems to call into this subsystem. So it has dependency directly towards it. So, but not necessarily when you have a dependency directed away from it. Then you don't necessarily need an interface for that. Any client using the interface is independent of the implementation of the subsystem. That is, you only need to care about the interface name, parameter, return values, not the internal implementation. So this is similar to the interface of a class, which consists of the set of public operations. here the interface is at a higher level, where you may have interfaces for each of the design classes, but you may decide to expose a subset of these operations as the interface for the whole subsystem. So course registration subsystem. So this is a blow-up of the course registration subsystem, as we saw in the previous diagram. This guy. So course registration subsystem. So now we look inside. So we see that it has essentially 4 classes. These classes are design classes, not analysis classes, but they're named also as by having a manager in the end, to indicating it's a control class. Request enrollment, manager has an I-enroll interface, so the convention is to have an I before the interface name to indicating it's an interface. Select courses to teach, manager has an I courses interface, and student registration manager has the I registration interface and I billing interface for the prepare billing information manager. So this is 4 interfaces. So we can use the facade design pattern. Remember, the facade is to have one class acting as the entrance, as the outside view of the entire subsystem. So we can have a course registration manager class as a new class, perhaps just an empty shell to redirect the calls from the outside that calls into the other classes, the other 4 classes, and expose a unified interface to the outside with the I course registration, which is perhaps a union of the previous 4 interfaces. So in this way, you minimize coupling, because now you expose one unified interface, and every time you update the interface, you just need to update this one class. So it enhances encapsulation because the outside now has a more limited view of the subsystem. So that's a facade class. So now we move upwards to the architecture design. So class design and subsystem design are both job of the component engineer. That is someone that works at a lower level abstraction. But now we're going to look from a higher point of view, from the architect's point of view, and see how to design the overall architecture of the system. So this is the deployment model. That is, it describes how the functionality of the system is physically distributed to processing nodes. So this is the notation for a node, computer node. So it can be a laptop, can be a powerful server. So deployment diagram shows nodes, that is computational resources like a processor, relationships, that is means of communication among the nodes like a network, and design issues include which nodes are involved and what are their capacities in terms of processing power and memory size. So is it a laptop, is it PDA, or is it a server with perhaps a supercomputer? So, and what type of connections are there between the nodes, and what communication protocols will be used? So is it a high-speed optical connection, or is it a Wi-Fi connection, or is it Ethernet? So what are the characteristics of the connections and communication protocols in terms of bandwidth, availability, quality, etc.? Obviously, if you have an internet connection based on a physical network, it has higher bandwidth and availability than perhaps a Wi-Fi connection. Is there any need for redundant processing capability? That is, you have redundant servers that may take over if something fails, failover nodes, and perhaps for load balancing process migration. That is, you can migrate a process from an overloaded machine to another underloaded machine to achieve more balanced workload and higher performance. Keeping backup data, that is, if the data is critical, then perhaps you need to keep a hot backup. That is, typical backup is when you do backup at the end of the day, perhaps you need to keep backing up data, keeping redundant data as the during daily operation by writing to a true copy of the database. So here is the ASU example deployment model, where you have the server part consisting of a web server and the database server. So these two can be on the same machine as perhaps in your implementation, but they can be in separate machines in a real system to balance the workload. The web server perhaps runs Apache or some other web server, and database server is the Access or Microsoft SQL Server or Oracle. They're connected via the internet. So that is the network within the company. It has high availability, bandwidth, and security. While the others, like the dorm computer, the main building computer, perhaps you have kiosks in the hallways, library computers, and register computers. They're connected to the web server via the internet. So this is the really a classic three-tier architecture, where you have the client connected to the web server via internet, and the web server connected to the database server via internet. So now we need to decide how to deploy the subsystems onto the nodes. So we happen to have, remember the all the subsystems in the middle of the three layers: security, people maintenance, cross registration, cross maintenance, report generation. So you put these subsystems into the web server node, and you put the user interfaces subsystem into the dorm node. And yeah, so that's a pretty obvious deployment model. That's fine. Just, yeah, I'll take care of it. So deployment is essentially by mapping from design subsystems onto physical computer nodes. So system design, we have finished this chapter. Now retrospective. So use case design identifies additional classes needed to meet design goals and handle the implementation environment. So we discussed use case design before in the requirement stage. Now, in the design stage, when we do use case design, we're identifying additional classes for implementation-specific issues, like OS and middleware and the hardware capabilities, etc. Class design is to complete a specification of each class in terms of its attributes and operations. So we did some class design in the analysis stage, where we identify the attributes of each analysis class, but now the attributes in the design class should be more concrete. it should be in terms of the programming language types. So instead of abstract type analysis class, so now I should say it's a double, it's a floating point, or it's a short. Operations should be more concrete as well. That is, you can directly generate programming language code like C++ or Java from the design model attributes and operations. Identify reusable components and restructure and optimize the design model. That is, now you need to consider performance. So you need to perhaps add some attributes and perhaps add some new associations, bypass layers, and do a bunch of things to improve the performance while keeping the functionality the same. Subsystem design includes subsystems and their interfaces. Organize the classes into cohesive, loosely coupled units. So this is to facilitate future implementation. Cohesion refers to when it describes does one thing and one thing well. Loosely coupled means that it has as few associations with other subsystems as possible. And finally, architectural design is the deployment model. So outlines the deployment of the system into processing nodes. Which subsystem gets mapped, gets implemented onto which node, specifies the physical distribution of the subsystems onto nodes. So now the design model contains use case realization / design. So this is opposed to the use case realizations / analysis. So now this is used to construct builds during implementation. So a build is a compiled executable that's perhaps done daily to have an executable baseline for the next build. So design classes, their operations, attributes, relationships, and implementation requirements. So these are in contrast to the analysis classes, which are more abstract. There's often one-to-one correspondence between design class and an analysis class, but there's it's also possible to add brand new design classes that's not in the analysis model. Implemented by files containing source code later in the implementation stage. Subsystems, their dependencies and their interfaces, implemented by implementation subsystems later in the implementation stage, containing source code, scripts, binaries, executables, etc. So, and finally, deployment model used to assign subsystems to processing nodes. So this is documented in the system design specification, SDS. So from that, you can do implementation, as we discussed in the next chapter. So, okay, so we're now finished with design. Implementation is a short chapter, even though it takes up perhaps the bulk of your time, because the theory is simple. It's just a lot of dirty work. So the idea is to understand what implementation is. Implementation is the realization of the system design model. Know the major activities that take place during implementation. So unified process. So I think there's a unified process diagram. No? Yeah, see here. Unified process implementation view. So now the implementation happens mainly during the construction phase, mainly in this phase. There's a little bit of implementation in the inception and elaboration phases for prototyping, and some implementation in the transition phase for bug fixing. But the main implementation takes place during the construction phase. So now again you see the division between the component engineer who is responsible for low-level component implementation and architect who is responsible for the high-level architecture issues, and system integrator who is responsible for integration build plan, that is building a system consisting of many subsystems. That's called integration. So class implementation. So a implementation of a class is called a component. It's a physical replaceable part of a system that packages implementation and conforms to and provides a set of interfaces. So here the interfaces are represented as the small rectangles sticking out of the large rectangle. So components may have stereotypes. Stereotypes are the additional annotations to indicate that what it does, what it is. So it may be executable component, it's a binary executable, or it's a file with source code, it's a library, either a static or dynamic library. So a static library must be linked at compile time, while a dynamic library can be linked at runtime. So that's the so-called DLLs in Windows. Table, a database table can be a component. Document, like a user's manual, can be a component. So you may have, say, two classes in the design model. They may reside in a single file. So this is the link between the design model and implementation model, the traceability. So each component may contain many classes and realize many interfaces. And there may be dependencies between components. That's the dependency. If the components are files, then the dependencies are compilation dependencies. That's described in the makefile. So class implementation, the goal is to implement a design class in the file component. So first you assign design classes to file components. The source code for design class resides in the file component, and the file component scope determines which design classes to include. So how classes are assigned to file components is determined by the facilities available in the programming language. For example, in the Java environment, you have .java file file component for each class. Say if you have Hello World class, then you must have a hello world.java file for it. Otherwise, the Java compiler or interpreter will complain about mismatched names. But in C++, you have more flexible assignments where a file can contain an arbitrary number of classes. And then generate source code from the design class by implementing methods for each operation. Remember the distinction between operation and methods. Operation is the interface classifier, and methods are the instance, the actual code behind the operation. So up to now, from requirements to analysis to design, we have been drawing these boxes, drawing these diagrams with the operation signatures on them, but we never discussed how the internal of each operation is actually implemented. Now's the time to write the code to actually realize the operations. Choose a suitable algorithm and supporting data structures. So if you have a sorting operation, then perhaps if you choose quick sort, it's faster than bubble sort. We're guided by flow of events in the use case model. So activity diagrams and state machine diagrams, all these can affect your implementation. Especially state machine diagrams, they can be directly translated into source code, either manually or there are automatic code generators that can take a state machine and generate C++ code or Java code from it. So subsystem implementation is when it's implementation subsystem. This is opposed to a design subsystem. So this organizes artifacts of the implementation model into more manageable pieces. Can consist of components, interfaces, and other subsystems, that is, other implementation subsystems. Each design subsystem is implemented by an implementation subsystem. That's a one-to-one traceability relationship between these two. So this is as opposed to the traceability between the analysis packages and design subsystems, where there can be a one-to-one correspondence between an analysis package and design subsystem, but you can also create new design subsystems that have no counterpart in the analysis package. But for implementation subsystems, you should always have a one-to-one correspondence with the design subsystem. Each implementation subsystem is normally implemented as a component. So a packaging mechanism is needed in the implementation environment. For example, package in Java, that is .jar file. You may package many .class files into a .jar file as a implementation package, which then you can distribute to your clients. Website project in the ASP.NET, VisualBasic.NET, where each project consists of all the collection of artifacts like the source code and all the user interface elements into a single thing that you can compile into executable. Directional files can be a packaging mechanism. This is more elementary, where you group related classes into the same directory, into the same folder as a package. So for the you call the ASU subsystem design we saw before, we had all these subsystems with 3 layers. Actually 2 layers, where the user interface is one subsystem that calls into the other subsystems in the application-specific layer. So in the implementation model, you really have a one-to-one correspondence between the design subsystems and implementation subsystems, also called components. Each component implements a subsystem. So now you have you draw the interfaces with the lollipop shape with the interface name, and each dependency coming into a subsystem must be pointed to the interface. So that is the user interface's subsystem. So this subsystem happens to be called the name user interfaces. It has its own interface called I user interfaces. So the interfaces, the word here is really part of the subsystem name. Well, the I in front of the user interfaces refers to the interface of the user interface's subsystem. So now this dependency must be pointing to the interface of the subsystem, but the dependency originating from a subsystem doesn't have to originate from the interface. That is, you can point from the internal of the user interface subsystem into the public interface of the system security subsystem. So that's the connections are also have one-to-one correspondence with the design model subsystem connections. So as you can see, the design model is really close to implementation. That's why you need to take into account all the non-functional issues so that the implementation can be a straightforward mapping into the source code. Obviously, the mapping of the interfaces are very straightforward, but the internal implementation of each operation may take you a long time. System integration. So this is when you do builds. So a build is the implementation of a part of the system's functionality. So each build is version controlled and allows rollback to previous versions. So you may do daily builds, or you may do weekly builds, and you have assigned a version number so that you can roll back using a version control system. Each lifecycle iteration in the construction phase will result in at least one build and usually several builds. So if you recall the construction phase, so in the construction phase, you may have several iterations. So here we have 1 to 3 iterations. Each one typically results in one build or more builds. So, but not in the other iterations, only in the construction phase. So integration build plan is the sequence of builds required in the iteration. So integration build plan specifies the functionality expected to be implemented in the build. So you may have, say, you have a 5 build planned, and you should place the most important use cases and scenarios into the early builds, and then put the less important ones in the later builds, so you can detect critical problems early. And also the subsystems and components required to implement the build. So this is the this requires you to have the so-called traceability between the functionality in the requirements model, that is use cases and scenarios, and the artifacts in the design and implementation models that correspond, that implement the functionality in the requirements model. So we'll discuss different integration strategies in the testing workflow in the next chapter. Because integration is not simply compile. Testing is a very important part of integration. So, because integration stage is often the time when many bugs occur. And so you need to integrate testing tightly into the integration strategies. So now we move on to the architectural of architectural implementation. So this is the mapping of executable components onto nodes in the deployment model. So the focus is assigning physical component instances to node instances or components to nodes. So here, this looks very much like the deployment model where you're assigning subsystems in the design model onto the nodes. Here, you're assigning the components, that is executable components, onto the physical machines. Notice the different shape here. This is the component, while subsystem is the folder-like shape. And so now here's the one example where you have workstation running the game engine and the player interface, while you have the PC running the player interface only. The reason you may have a player interface component running on the workstation is perhaps for development and debugging purposes. And they're connected by a LAN. So this architectural implementation is the action of actually perhaps downloading your executable file into the node, while the deployment model in the design stage is drawing a diagram to indicate how to map. So implementation, that's very easy, right? So you have class implementation, where you implement a class, mainly the operation methods. That is the methods for implementing an operation, to be more precise. So you write the source code for a class that resides in a component. Component is an implementation artifact. Could be a file, could be executable file, source file, could be a library. So subsystem implementation organizes components into cohesive, loosely coupled units. Could be a Java jar file, could be a folder of source codes. Uses programming language packaging mechanisms. So system integration integrates all subsystems into the final system. So this is when you may encounter many headaches, many bugs that's not doesn't appear until you integrate these together, because typically the subsystems are developed by different developers, perhaps in different languages even. So the interfaces can cause many issues. So you need a test plan to ensure everything works correctly. So architectural implementation is to assign executable components to physical processing nodes. So this is you can do this directly based on the deployment model in the design model. So the implementation model contains the implementation subsystems and their dependencies, interfaces and contents, components and their dependencies. So the implementation subsystems may contain components and other smaller subsystems, mapping of executable components onto nodes in the deployment model, that is the .exe files if it's Windows, and architectural view of the implementation model in terms of which components get mapped to which node. So that's the end of implementation. Any questions? Okay, so we move on to testing. So the learning objectives are to understand the difference between verification and validation. Oftentimes, people use the two words in a vague manner. So there's actually a difference. Understand the principles of component testing and system testing. Component testing is testing at the small scale, and system testing is testing at the larger architectural scale. Understand the basic strategies can be used to generate system test cases, and understand the strategy for performing the different kinds of software testing. So, testing, the purpose of testing is to try to find the differences between the specified, expected, and the observed existing system behavior. So that is the difference between validation and verification. So validation makes sure that we have built the right product, while verification makes sure that we have built the product right. So validation, we check that the system meets its stated requirements, and each system function derives from some requirement. So that is, the system is doing what the requirement says it should be doing. And verification is to check the quality of the implementation by ensuring that each function works correctly and has no defects. That is, the system has very little bugs or has no bugs. So you can have a system that is perfectly bug-free, but it doesn't do what the requirement said it should do. That's you have built the product right, but you didn't build the right product. Or you can have a system that does exactly what the requirement said it should do, but it crashes every minute. So that is the right product. That is, it passes the validation, but it riddles with bugs and it doesn't pass the verification. So acceptance tests mainly deal with validation. That is, acceptance tests are the tests that derive from the requirements, typically from the use case flow of the events, for validating all the stated functionalities in the requirements. And most of the other testing workflow is targeted towards doing verification. That is, to ensure, to detect bugs and to improve the reliability and robustness of the system. So the goal is to design tests that will systematically find defects. So we discussed acceptance tests earlier in the requirements lecture. So this chapter, we're mainly focusing on verification testing. That is to identify defects and fix bugs. So the reality of testing is that testing cannot show the absence of software errors. It can only show that software errors are present. That is, if you test the software extensively and you find no errors, it doesn't mean that the software has no errors. That only means that you did not detect any errors. So you can only show that you can find errors, but not show the absence of errors. It is impossible to completely test a non-trivial system. By impossible, we mean impossible in a realistic time and cost budget. Of course, it's possible if you're willing to spend 1,000 years in testing. So most systems will have bugs in them that users uncover later. It's just a reality of life. If you aim for bug-free systems, then you'll never deliver the product. Testing is a destructive activity. It tries to make the software fail. That is, testing is attempt to break the software. So it's difficult for software engineers to effectively test their own software because they have no incentive to make their software fail. If their software fails, what happens? They do debugging, and they create more work for themselves. So that's why oftentimes the company, large company, has dedicated testers, test engineers, whose job is to stimulate, poke the software with different test cases and try to make it fail. So good testing has the opposite nature of good software engineering. So good software engineering tries to ensure that software does not fail, and good testing tries to make the software fail. So therefore, you often need different people for doing testing than for doing the developing. But oftentimes, especially in a small company, the developers also do testing. So. And it's actually interesting that many people view testing as somehow a lower level skill than developing software. And typically a tester is someone who doesn't have the skills to write code. Then he's assigned to testing, right? So it's really a prejudice against testers. Say in Microsoft, they have testers for life. A tester can be doing testing for all his career at Microsoft, and it actually can involve a lot of skills. So testing has this really lumpy shape. So it really happens all through elaboration, construction, and transition phases. So now you have the test engineer who's responsible for the test cases, test procedures, test plan, test evaluation to see if a test passed or failed, and a component engineer for testing the component itself. So that is, when you're writing code, it's a good idea to write small test cases to test the code while you're writing it. And then the tester's job is to test the higher level testing, the architecture level, integration level. So the component testing is better done by the component developer, component engineer. So their integration tester and system tester are responsible for finding defects. So plan tests. So why do you need to plan tests? Why not test your software exhaustively? So consider this flow chart that is perhaps activity diagram describing the internal implementation of a operation correspond to a 100-line program with a single loop that may be executed no more than 20 times. So this really should be loop less than or equal to 20 times. So it can be just depending on your code, conditional switches, you may loop less than 20 times, but perhaps sometimes you loop for 20 times. Now, how long will it take to exhaustively test this program? It takes this many years to test the program. Each test requires 1 millisecond. Why? Because you have a combinatorial explosion of the possibilities. Consider how many paths you have at each loop iteration. You have this one. This is the second one. And the third one. And the fourth one, and the fifth one. So essentially you have 5 choices, 5 paths each time you go through the loop. And then you have, say, 20 loop iterations. So how many possible paths do you have? You have 5 to the 20th power, right? So if you do a simple calculation, in Google you have a calculator. So 5 to the 20th power, it is 9 to the 13th power. So it's essentially 1 to the 10 to the 14th power. So this is a huge number. So if you convert it into milliseconds, how many milliseconds are there in a day, etc., it turns out into thousands of years to do the exhaustive testing for the trivial small example. So this illustrates it's impossible to test any realistic software exhaustively. So that's why you need test plans. Is to design a set of tests that has the highest likelihood of uncovering defects with the minimum amount of time and effort. So try to direct your tests at the most suspicious parts of your software and try to maximize the likelihood of uncovering defects while making no guarantees, because it's not possible to make any guarantees. So tests cost money and take time to develop, perform, and evaluate. Up to 40% of project effort is devoted to testing. So a test plan specifies a strategy, the estimate of the resources, and a schedule for testing, when to run which tests. So the strategy includes the criteria and goals of testing, including what kind of tests to perform and how to perform them. We'll discuss different kinds of tests like white box, black box, integration testing, etc., and provide level of test and code coverage. That is, how much of the code have you covered? And percentage of tests that should execute with a specific result. And based on the strategy, you can estimate the resources needed, like the people resources and monetary resources. And finally, you come up with a schedule when to run which tests. Okay, we'll see you next time.